All right, got some ideas on these? So with these types of questions, the main thing is you got to figure out what you're given and then what you're asked for. There's a lot of times I see mistakes on these that like people kind of knew what they were doing, but didn't really read the question that way. So in this case, the question is asking how many moles of carbon, and then what you're given is half mole of SO2, 0.500 moles of SO2. So you're always going to start with what you're given. You take your 0.500 moles of SO2, and then the goal is to figure out carbon. So your mole to mole factor is going to be moles of SO2 to moles of carbon, because that cancels SO2 and instead gives you carbon. The numbers you get from that are read in the equation. So it's 5 carbons to 2 SO2s. I think that comes out to 1.25. Right? So then the second one's done the same way. We just start with a different thing. So we're going to start with that 1.2 moles of C. And now we need a factor that gets us from moles of C to moles of CO. Because the question again is, how many moles of CO2 are produced? We can use those numbers from the question again. So 4 of these, 5 of these. And what does that come out to? And that's the moles of CO. So if it's just moles to moles, it's that one factor, just using the numbers in the equation to get that. Where there's the extra steps is when we have to convert to mass. When we have to go to or from mass instead of moles. So let's try that. That's the next section here. This was one that was on a quiz. So let's look at those two. Another reaction now. How many grams of H2O are needed, to react with 75 grams of calcium cyanamide? And then the same thing for ammonia. How much ammonia is produced? So in this case, you're going to do the same thing as before, but in order to get to moles, we have to convert grams to moles, and then we have to do the same thing at the end because the question is asking for grams. So see if you can do this one with those extra factors in there. Thanks. All right, got some numbers here so far. Yeah, I think something sounds about right. So the way we set this up usually, we just kind of put them all together, grams to moles, then moles of one to moles of the other, and then moles to grams to get the final answer. So that's the grams that you're starting with here. 75 grams. And when you do these things, I think it's really helpful, even though it's a little tedious, to label all the units, like grams of this, moles of this. It just stops you from getting confused or from putting the wrong number in somewhere. If you just leave it, if you keep doing it that way. And then also when I'm grading it, I'll see, oh, everything's okay, but they just put the wrong compound there or something. And then you won't lose as many points. So we're going to go to from grams of CaCN2, just like any other conversion. We cancel on the bottom or cancel on the opposite side to moles. Then moles of one to moles of the other, which in this case is water. And finally, moles of water to grams of water. All right, we put in the numbers. The moles of water to moles of CaCN2 we get from the equation, 3 and 1. Water I know is 18 grams per mole. CaCN2, anybody calculate that? 80. All right, so then we can calculate through. 75 divided by 80 times 3 times 18. 51, 50.6, we'll say. Water needed. All right, hopefully you got something like that. So for the next one, we're going to use the exact same technique. Oh, whoops. We're going to use the same technique and just change it based on the other type of a question. So all I need to do here is change. We're still starting from CaCN2, so that part's going to stay the same. Oh, that stays the same, actually. This changes because we're being asked for something else now. We're being asked for NH3 instead of H2O. All right, so let's adjust that. Now we're NH3, NH3. We're starting this time with 5.24 grams of this stuff. And then the equation tells us that the mole ratio here needs to be 2 to 1. And ammonia is 17 grams per mole. Okay. Otherwise, it's the same. 5.24 divided by 80 times 2 times 17 is 2.23. NH3 produced by 5.24 grams CaCN2. So these types of questions always the same like that. And I did put some in the exam where, because I know when we did on the quiz, sometimes you'd have to come up with the equation yourself. There's some of that, but there's also some where you're given all the information. It's just like that. So hopefully you can do that all right. All right, so that's part of the exam, the polarity stuff. What else? Yeah.
I actually had a question from the lab report.
Yeah.
That I don't understand.
Sure.
An isotonic solution of NaCl is 0.9%.
Oh, yeah. I said we were going to go through that one in class. Let me pull that up. There's a couple of questions on this lab that are kind of beyond what you should be able to do. So let's go through them together, as long as we're here. Okay. They are. All right, so we didn't really talk about mass by volume percent mass by volume. So let's just go through some of these here. It's basically all of these. Okay. So this first one, mass by mass we talked about. The mass of the solute divided by the mass of the solution. So you can do that because you're given the mass of the solution and then you're given the mass of the solute, and that's what we did during lab 2. But this middle one, mass by volume, we didn't talk about, and that won't be on the exam either. So let's just talk about how to do that. It's also a percent. So it goes grams divided by 100 milliliters. Another way to think about that is grams divided by milliliters times 100. So in this case, that would be 4.78 grams divided by 25.00 ml times 100%. So that's 4.78 divided by 25 times 100% is 19.1%. And that's percent mass by volume. So it's similar, it's just like the mass percent, but you do it with volume on the bottom. All right, so where that gets tricky in these next couple. So let's go through these together. How many grams of calcium chloride are in 10 milliliters of a 5% mass by volume solution? So in a mass by volume solution, that means, so 5% means 5 grams per 100 milliliters. So 5 grams of solute per 100 milliliters of solution, that's a 5% solution. Because 5 divided by 100 times 100% is 5%. That's the definition of that. The way we figure out this kind of a thing, easy way to do it is just from a proportion. So the concentration has to stay the same whether you have 100 milliliters or 10 milliliters. So if you know there's 5 grams per 100 milliliters, we can say how many grams are in 10 milliliters. And you end up getting 50 divided by 100, which is 0.5. Makes sense. If there's 5 grams per 100 milliliters, 5% of 10 is 0.5. That's another way to think of that. So that's how you deal with mass by volume percent. Again, that won't be on the exam. Okay, the next one, this one's a little tougher. An isotonic solution of NaCl is 0.9% mass by volume. So again, that 0.9% mass by volume means 0.9 grams of NaCl in 100 milliliters of solution. And then it's asking for what is the molarity of that solution? Well, what's molarity?
Moles per liter.
Moles per liter. So we need to get somehow from grams per milliliter into moles of NaCl per liters of solution. So can we get from grams to moles? Yeah. Can we get from milliliters to liters? Yeah. So that's how you do this. You convert the grams to moles. So you go 0.9 grams NaCl, grams to moles based on the weight. So that's 23 plus 35.5 is 58.5. 0.0154. Okay. And then 100 milliliters. We know there's 1,000 milliliters in 1 liter. So that's 0.1 liter. Oops. Solution. So the molarity is the moles divided by the liters, so 0.0154. Which is 0.154 molar. NaCl. So we had to go grams to moles and then milliliters to liters. Let's take a look. Are there any other ones that you can do? You can probably figure out their cities. Yeah.
Iodine and vegetable oil are not soluble in water because they're non-polar.
Right.
And water's polar.
Yep. And so they have different types of forces. Yep. And this lab, by the way, is due a week from Wednesday, not Wednesday. What else are we going to go over? Other questions? World Series predictions?
For molecular compounds,
Mhm.
it says that valence electrons are shared by nonmetals to achieve stability.
Mhm.
But how do you figure that out? Like,
In what sense?
like how do you know something's like a molecular compound?
I think the easiest way is just to look what types of atoms are in it. If there's metals involved, it's not molecular. Let's look a little bit at because it's kind of like with the naming too. If you have something like KCl, you see the K, and that's a metal, and that tells you this is an ionic interaction. So that's ions. If you see CO2, there's no metals there. So that tells you that's got to be molecular or covalent. And that tells you that the C's and the O's are bound by covalent bonds, those sharing of electrons that you talked about.
So do they like complete each
Yeah.
other's valences?
Right. Mm-hmm. Yep. So like carbon has 4 electrons and oxygen has 6. So they can share. They actually have to share more than that. Didn't really draw that in the best way, but those have to share 2 pairs of electrons on each side. And then what you have, we'll redraw this a little bit less ridiculous. So now you would say that since those middle ones, the ones in between are shared, we would say that this oxygen has 8 electrons around it now. This carbon has 8 electrons around it. And this oxygen has 8 electrons around it. And that's only going to happen with nonmetals. Now, you can have compounds that have both that we've seen. So things like this. We talked about K2CO3, potassium carbonate. That's an ionic compound because you've got potassium ions and you've got a CO3 ion. We didn't really get into this too much, but that itself is actually a covalent compound. The carbon is bound to the 3 oxygens through covalent bonds.
Covalent means positive and
Means sharing the electrons,
oh,
like in the CO2. So that's an example of a compound that has both ionic and covalent bonds. Now, practically, we call this a covalent or an ionic compound because that's what's most important about it, is that it has those ions, it's an electrolyte, all that stuff. But if you're really looking deep inside it, there are actually covalent bonds inside this compound. But if I said, okay, the question was, which of these compounds is a molecular compound or is a covalent compound? You would not pick this one because it has a metal and therefore it's really ionic. But if it said which of these compounds contains at least one covalent bond, then this would count for that. I probably wouldn't ask you that.
so with electrolytes, they have a stronger electrolyte would have more positive ions or
No, just a stronger electrolyte can break up into ions, can break up into pieces more. So some compounds, when they dissolve in water, they completely break apart into ions, and other compounds don't. They stay together, and the water goes around them. A strong electrolyte is one that breaks apart into those ions. And a non-electrolyte doesn't. So something like sugar is really soluble in water, but it doesn't break apart at all in that water. It stays whole sugar molecules. So it's not an electrolyte. It doesn't make any ions. But something like K2CO3 would break apart into ions in water. And so that would be an electrolyte.
on the report sheet also for the solute I2.
Yeah.
Because then it's non-polar. Is that because there's two and they're both negative?
No, they're covalently bound together. Yeah, right. So it's, if there's no metal there, that's a covalent compound. So it's 2 iodine atoms connected by a covalent bond. Because they're the same kind of atom, the electrons don't get pulled more to one side or the other because it's the same atom on both sides. So the difference in electronegativity is 0. And so that's a nonpolar compound. The electrons aren't being pulled more to one side or the other.
me do this problem. How many moles are in 650 milliliters of a 0.80 molar solution? If you first convert milliliters to liters,
Yeah. So say that again. How many moles?
are in 650 milliliters
Yep.
of a 0.80 molar solution.
Yeah. So 0.80 molar means 0.80 moles per liter. So if we don't want to know how many moles are in 650 milliliters, we need to be able to convert that.
So 0.6.
Yeah, so we would say 0.650 liters times 0.80 moles over 1 liter. Liters cancel. End up with 0.65 times 0.8, which is 0.52.
Are we gonna need to know how to draw like the graph for energy and chemical reactions? Like the activation energy and
Yeah, you should know what those are.
we go over it.
Sure. Well, here, let me grab it from the book so we can see the pictures. Okay. So here are basically the two types of graphs of reactions. You've got the progress of reaction on the x-axis, so going that way is going forward in the reaction from reactants to products. Energy of reactants, energy of products. Either it's going to be exothermic or endothermic. So if it's exothermic, that means that the reactants are higher energy than the products. When you go from reactants to products, you lose energy. If it's endothermic, you gain energy going from reactants to products. So you have to put energy in to do that. And then there's this hump in the middle that's the activation energy. So that's how much energy it takes to get the reaction started before it can keep going. So these two graphs pretty much tell you all you need to know about those things. I'll put them in the notes here. So you've got here the heat of reaction, which is the difference between the energy of the reactants and the products. And then you've got the activation energy, which is the difference between this point and this point. And those are the two different situations. The activation height is proportional to the speed or the rate of the reaction. So if you have a higher hill, you have a slower reaction. And that's why adding a catalyst lowers that hill. Maybe does something like this. So you end up with the same reactants and products, but you have lower activation energy.
I don't get like why is the energy of the products lower in the
In this case, because the first one is an exothermic reaction. So that means the heat comes out. If something's at a higher energy level and it moves to a lower energy level, the difference, all that rest of that energy has to go somewhere, so it goes out.
What exactly does activation energy mean?
It means you have to put in a certain amount of energy to get the reaction going. It means without that energy, this reaction won't take place at all. Even though it's exothermic, it won't start without a spark or something. Something to get it started before it can release that energy.
So then endothermic would take heat in? Or?
Right. So you still have to give it extra energy to start, but then it can continue and go, but then it would take heat in. So it would feel cold because it was sucking the heat in from the surroundings.
Why would it feel cold if it's taking?
Because that's what feeling cold means, is it's sucking heat out of your finger, let's say. So if your finger is against this reaction, it's taking the heat out of your finger.
Oh, so you would feel cold.
So you would feel cold.
The actual thing would be hot.
No, the actual thing would be cold. It's really confusing because the molecules themselves are what's doing this. So they're taking heat from, let's say, the solvent, the glassware, all that stuff. So anything that you're actually feeling, so yes, the molecules themselves are raising their energy, but all the surroundings are becoming colder. So when you touch it, it feels colder. Like the solvent that the reactants are dissolved in, the glassware that it's in, all that stuff is getting the heat sucked out of it, so it feels colder. We don't actually feel like the reactants themselves. But yes, it's confusing. Yeah.
Can we go over like writing the products, like when or writing the reactants when you're adding two products together? How do you know?
Oh, like how do you know what it's going to make?
You put the cation with the anion.
Yeah, we can try one of those. So let's say it's a good example. From what? Oh yeah, is there a good one on there? On the practice exam?
Says in the chemical reactions lab, you mixed cobalt, Roman numerals, numbers of 2, nitrate with sodium hydroxide. Write a balanced equation for this reaction.
Oh yeah, okay. So write a balanced equation for this reaction and figure out what's happening here. So first step is to categorize it, because a lot of reactions we can't predict. Like we don't know the answer to this question. So to make sure it's in one of those categories that we can predict, we have to figure this out. So what kind of a reaction is this?
Double replacement.
This is double replacement. Yeah, how do you know?
There's no combustion.
Right, there's no combustion, there's nothing by itself. It's pretty much the only thing left. It's another way to look at it is it's two ionic compounds. If two ionic compounds react together, that's a good bet as to what that's going to happen.
What about to displace from a decomposition? Like, how do you know if it would not be a decomposition? Does it have to have like an acid or some kind of oxidation?
Usually the decomposition reactions we see just start with one reactant and then it breaks down into multiple products. So that's how you'd see that one. All right, so you got two ionic compounds. You can assume this is going to be a double replacement reaction, which means the cobalt is going to go with the OH and the sodium is going to go with the nitrate. But you can't just pull the things apart and stick them together, because we have to think about the charges and how many of each ion we have. So let's pick one of those pairs to do first. So the cobalt is going to go with the OH, and maybe it's helpful to just write down those charges so we know them. Cobalt is 2+ here, and hydroxide is -1. And then in the other case, sodium is +1, and NO3 nitrate is -1. So now we can build new compounds based on that.
How did you know that cobalt was 2+, if it's in the transition
Yeah, in the question it said cobalt 2. You could also tell from here though, because you know nitrate is -1, and there's 2 of them, so cobalt would have to be +2 to balance that out.
Joe, I have a question.
Yeah.
So if we're dealing with one of those transitional elements, if it has a valency as a reactant,
Mhm.
it won't change its valency in the final product, or can it change?
It won't in this type of a reaction, and it won't in any kind of reaction that is predictable to us.
Okay.
It can, but that would be a redox reaction. That would be something different would be going on. So there isn't always a good way to predict that. So I wouldn't expect to see anything like that. Yeah, if you see something with a charge in this type, in a double replacement type reaction, you can assume it's going to keep its charge. Yeah. All right, so let's put these compounds together. What would a compound between cobalt-2 and hydroxide look like?
COH2 with OH.
Yeah, so we go COOH2. And then what about sodium and nitrate?
You can just go together.
They can just go together because they're +1 and -1. So that's the products. Is that equation balanced? Not yet. So let's balance it. We can balance the nitrates first, and then sodiums with hydroxides. I think that's it.
Can we do a couple of those practice-wise?
What?
Can we do a couple of those practice-wise? Just like-
Sure. On. We'll do it with words, so you have to draw the compounds too. So cobalt-3 chloride and silver nitrate. I do have to give you some information in this one. Silver is always +1. That's not one that you need to know, so I'll tell you. Silver is +1.
So for the products, would you just write COCl plus AgNO3, or do you have to do the charges and stuff?
You have to do the charges and
Okay.
stuff, yeah. Make sure that your compounds are always neutral.
So since cobalt has a 3+ charge and nitrate has a -1 charge, when you write the product side, would you write then CO3?
Close. I was with you all the way.
CONO3.
3, yes, there you go. Yeah, so this one would be COCl3 plus AgNO3. And then you switch. So the cobalt goes with the nitrate, but it's still +3. So it has to go cobalt NO3, 3. And then the silver goes with the chloride. So that's not balanced. So we have to do that to balance it. The other thing I would want you to be able to do is the combustion reactions. We've done those on a couple of quizzes now. So if I said something like glucose, which is C6H12O6, undergoes combustion. To be able to draw an equation for that or write a balanced equation for that. Let's see if you can do that.
Don't you always get CO2 and H2O in the combustion?
Right. Yep. Yeah, that's how you can write an equation like this with such little information, is you've always got the same. Combustion means reaction with oxygen, and then the products are always CO2 and H2O. So C6H12O6 plus O2. So then you have to balance it. Oh wait, that's not right.
No.
Nope.
Correct.
Wait. Now I'm confused.
6 in front of that too.
Should be a 6 here, right? Yeah. Right.
So it just means it reacts with oxygen, so you just add oxygen to it?
Mm-hmm. Yep, that's it. So also with that then, if you see something where it's just like some carbon hydrogen thing plus oxygen, that's a combustion reaction. Always.
So if it's just those three in the reaction, then it's gonna be a combustion? If
Yeah.
CH and O?
Well, that's a little too general, but probably for our purposes, yeah.
Okay.
Anything else?
About the single replacement.
Single replacement, yeah. Let's take a look at that one. That was a little trickier. Some you can tell and some you can't, which is the issue with that one. But let's look at something like, well, let's see. Here, let's see. Yeah, they always kind of give the same example that we used in lab too. All right, so take a look at this one. Magnesium metal and zinc nitrate. So you can see this is a single replacement in that there's one thing by itself and then a compound of two things. So that means the products are going to be that single thing going with one of the two parts. But then we have to decide, is the magnesium more likely to go with the zinc or more likely to go with the nitrate? Nitrate. Yeah, you're right. Why? How do you know that? Right, we don't usually see these. It would be a pretty tricky question if it was metal going with another metal and then the other ion thing going off by itself. So that's probably unlikely. So then we can write this as Mg, and in this case it has the same charge, and then zinc metal. Because both metals have the same charge as ions, there's it's already balanced and everything. Where this can get a little bit trickier is in like what we did in lab, which is also an example in the book. When you put some metal in HCl, same idea. The Mg is going to go with the Cl and the H is going to be on its own. But yeah, it's going to turn to H2 because whenever H is on its own, it's always H2. That's one of those diatomic gases. And then the other parts, it's not just going to be MgCl. What's it going to be? Yeah, MgCl2, because we know magnesium makes a +2 ion. So this one is not balanced, so we have to put a 2 here. That was one of the reactions from lab also.
What dictated the magnesium pairing with the chloride?
Instead of the hydrogen? Yeah, that's one that's tough to predict. You could say it, you could think of, since HCl is an electrolyte, like we talked a little bit about that as acids, you can think of it as the H is kind of like a plus ion, like it's in the same column as all those other plus ions. So when H comes first, it's often like a positive ion. You can also just, from experience, like, and I don't mean like life experience, just like in this class, we've seen compounds of magnesium and chloride. We haven't really seen anything of magnesium and hydrogen. So if you had to pick, that would be the one that's probably most common or most likely.
So whenever the H is by itself, it's going to be H2. Is that true for oxygen too? Like it's always going to be O2. It's never just going to be O. Right.
So it's true for H, NO, FCl, Br, and I. They're always two together as two, never just alone as an atom. Does anybody have any good, like, clever cheating methods planned? Just curious. Cheating methods, like, maybe come up with some new device that you can project the answers on the back of your eyelids or something. Do you know about the bottle of Coke trick? You ever tried that?
No.
So you put the answers on the inside of a Coke label, like on a bottle of Coke, and it's it's brown, so you can't see it. But then when you drink it, it tips, and you can see what's on the label.
Where have you been many years ago?
We all have a Coke bottle.
Right. Yeah, everybody shows up with a Coke bottle on Wednesday.
I'm gonna do Dr. Pepper instead.
What?
I'm gonna do Dr. Pepper instead.
You're gonna what?
I'm gonna do Dr. Pepper instead.
Oh, okay. You gotta be careful because Dr. Pepper should be okay. Some of the drinks come in like darker colored bottles. It wouldn't work as well. Or you just do it with like spray and you can just see it all the answers right through there.
Instead of seeing numbers and letters in our drinks.
Yeah.
Oxidation becomes more positive. Right?
Yes.
What about this one sheet you mentioned that works really well?
What's that?
Staying up all night and reading the chapter over and over again.
Yeah.
It's not the best way to do
I heard getting sleep the night before was more effective actually.
it. That's working hard, that's smart.
Yeah. It's true. Yeah.
Obviously, the third exam is going to be the same way it's going to be from the beginning all the way up to the end.
I'd say yes with like a little asterisk. The stuff we're gonna do after this chapter is a little bit more like doesn't depend as much on stuff from before. So it won't be as much as like this one.